I'm gonna wipe right now here. Okay. Here's white. I just have my
Oh, yeah, I got to follow. Yeah, I just bought a vlog camera. Yeah, what kind of camera you have? Oh, yeah, we got it. Nah. Probably wasn't for me. Calculate Oh, you did? Oh, nice. Oh, really?
I don't know. I don't. I'm sorry about that.
Oh, no, I'm not. We're right here.
Stop the rage. Now you're on stop. I got delicious white milk pepper and cheese. I sell stuff. I don't like I'm not like a power seller. Like I mean, saw a couple things that I'm selling. So
Lauren, I see you.
I apologize about that.
No worries.
Problem with you.
For sure.
What the fuck do you do? Alright. It's a little hot, so you can try that.
This is the first one I was they said I got like a nice pink color. Yeah, I was chilling though. Upside. And I heard you take the car. You know you do the yeah. So I got the yellow car. My car and I went to the garage. I'll be chilling. I don't know. Mine is I tried it, I put it, it showed up as 8 HDMI 1 or 2, whatever. HDMI 2 showed up. I clicked on it, it says nothing. So I'm like, alright. No, the thing is on, turned off. Like when you turn, I had it on, when you connect it, boom, the screen is blank. So like, alright, it's connected. I didn't see nothing. So I was like, let me try it again. No, I know, but you know when it pops up? And that's just shit. And that's the what?
I was give my 4.
Have a long ass AC right car from the room to the garage.
Well, thank you very much for that introduction and for all the kind words. It's such a great honor and a great pleasure to be here in Oslo and to receive this prize. I realized that there may be many people in the audience who are not fully trained number theorists, let alone fully trained mathematicians. So it may be that you don't understand more than the opening descriptions of the problem and perhaps the first few things I say about them. But there is no better way to understand the mathematical experience than to understand just the question and the opening statements. That's what we suffer every time we face a new mathematical problem. So I hope you will enjoy the genuine mathematical experience that will involve. So this is the Fermat equation that x to the n plus y to the n equals z to the n should have no solutions. As you all know, Fermat annotated a copy of a Greek text of mathematics, and in the margin he wrote, "It is impossible on the other hand, to divide a cube into two cubes, a fourth power into two fourth powers, or likewise, any power higher than the fourth into two like powers. For this, truly, I have a wonderful proof, but this margin is too small to contain it. He wrote this, we don't actually know when, because it was only after he died that his son republished the original Greek text with these marginal notes in 1670. And it is only through his son's intervention that we can actually know what Fermat was thinking. So we can't precisely date it. We don't really know whether he started to cross this out. But for a long time, people assumed he did have a solution and tried to find that solution, myself included. So the case n equals 2, of course, there are many, many solutions. We learn in high school 3 squared plus 4 squared equals 5 squared, 5 squared plus 12 squared equals 13 squared, and so on. These were known to the ancient Babylonians. Work on this problem of trying to extend this, or rather refute this in the general case to show that there are no solutions for n greater than or equal to 3, generated and in turn was inspired by many developments in number theory. The field of number theory in some sense started with Fermat himself. And there's a clear division in the attempts to solve this problem, which was parallel to a division in the subject of algebra, which was studied by Abel. So as you all know, Abel proved the insolvability of the general equation, the general quintic and more generally higher degree equations. And that marked an end of hundreds of years of study of algebraic equations, of solving equations using radicals. But this problem, solving equations via radicals, is an algebraic answer to solving equations. And what number theorists are looking for is a much more arithmetic issue. But actually, we get stuck at the same point that was resolved by Abel. So what did Fermat actually achieve? So what we have written evidence for are the cases n equals 3 and n equals 4. So in the case n equals 3, although it's not at all obvious, you can restate the problem as showing that there is no right-angled triangle where the sides have rational lengths, all three sides, and where the area is 1. So it's not obvious. You use the formula for the area of a triangle, and you can deduce this using Pythagoras' theorem, that it's equivalent to the case n equals 3 of Fermat's last theorem. So Fermat claimed this in letters several times in his life, particularly in letters to Digby and Kirkcaldy. The case n equals 4, he showed and actually described the proof of the case, actually something even stronger, that the sum of 2/4 powers is not a square. Fermat describes the method, and he called it the use of infinite descent. So unfortunately, we know rather little about exactly how he wrote out his proofs, he thought about his proofs, because he was still living in an era with rather limited publication. So in the Middle Ages, when equations were being studied prior to Abel in the 14th, 15th centuries, mathematicians in Italy would challenge each other by having mathematical duels where they would set problems to each other. And their reputation, their status, and their careers really depended on the outcomes of these duels. And I'm sure you know the famous history of the solution of the cubic. Well, there was a certain leftover inheritance of this in the way Fermat discussed mathematics. He would issue challenges to other mathematicians, particularly the English mathematicians, which they signally failed to understand or solve in most cases. So that's part of the reason that we don't have the detailed proofs, because he set his results as challenges rather than explaining the proofs. Well, this method of infinite descent, I tried to trace where it came from, and actually in 1636, Fermat knew nothing of number theory. He must have encountered some problems from the book of Diophantus, and his very first question, actually to Roberval, another French mathematician, was actually an extremely elementary question where he didn't understand the proof. But it actually reduces to a very famous classical, ancient classical proof of the irrationality of the square root of 2. So just to give an idea of how infinite descent works, I will show you how he might have thought of that proof in terms of infinite descent. So here is an actual proof for you. Theorem: the square root of 2 is not a rational number. So what you do is you start off by supposing the square root of 2 is a rational number, so you can write it as a quotient, a over b, where a and b are integers, like 7, 11ths, whatever. You choose a solution where a and b are both positive. Well, you can rewrite that as a squared equals 2b squared. And now a is even because it's twice b squared, so a is twice another integer. Substitute that in a equals 2a0 in the original equation, and you get 4a0 squared is 2b squared. Cancel the 2, you get 2a0 squared is b squared. That now tells you that b is an even number. So b is twice b0. Okay, now you do the same thing again, so you substitute in for b, b is 2b0, and you get a0 squared is 2b0 squared. And now you've got the square root of 2 is actually a0 over b0. So what you've done is you've taken the solution to the equation and shown that actually there's a smaller solution. And this new one has the a0 strictly smaller than a. Well, then he says, well, a smaller solution gives a contradiction because you can't keep getting smaller solutions forever. There's no infinite descent. So this is not how this is typically presented, but I imagine this is how Fermat came to the idea of infinite descent. And it's very striking that actually this idea of infinite descent was basically the foundation of all attempts on Fermat until the late 19th century. So now I'm going to jump mathematically to the next successful, partially successful attempt, which was by Kummer in the 1840s. So there was a lot of drama in this period where in the French Academy people announced proofs which were fallacious, and there was a lot of excitement, but actually it turned out to be, they turned out to be wrong, and they were wrong in a way that had already actually been explained by Kummer and published previously, a few years previously. So the idea is you again try and assume you have a solution to the equation, and then try and deduce from it a smaller solution. So what you do is you take the equation, the general equation, so it's z to the p is x to the p plus y to the p, well, that actually can be factored as a product of p factors like this, where zeta is e to the 2 pi I over p is a pth root of 1. So this is using complex numbers, we can just factor this as a product of linear factors. Now, the idea is, if you take a number which is a pth power and you write it as a product of other numbers, if those numbers are co-prime to each other, then each one itself has to be a pth power. For example, if I take, in terms of cubes, if I take 8 times 27, that number, there's no other way of breaking it up as a product of cubes. What does that mean? That means that essentially, if these numbers are co-prime to each other, then each one should be a pth power. Well, what do we mean by pth powers? Well, we have to work in arithmetic of z zeta. So we have to allow not just ordinary integers, but combinations of powers of zeta. And then miraculously, what you can do is you have this completely formal identity, x plus zeta y times 1 plus zeta minus x plus zeta squared y is zeta x plus y. Well, what's the use of that? Well, the point is that if each of these factors were pth powers, then this is a pth power times 1 plus zeta minus a pth power is zeta times a pth power. It's very similar to the original equation. And the idea of comma is, well, supposing we start with a solution here, and now we're probably going to start with a solution in z zeta instead of a rational solution, we can deduce that each of these factors are pth powers, and hence we get another equation which is very close to the original one. Maybe we can use infinite descent. We start with a solution, we deduce in this way that there's actually another solution which is smaller than the original one, and again, try infinite descent. Well, at first sight, this looks very tricky because this 1 plus zeta is in the way, this zeta is in the way. But it turns out that if you really study the arithmetic of z zeta, you can make this work. These are units. 1 plus zeta and zeta are both actually units in this, what we call ring of numbers, z zeta. Provided something is true about ideal class groups. So the problem is this principle that if you take a number like 72, that it's 2 times 2 times 3 times 2 times 2 times 2 times 3 times 3, there's a unique way of factoring any number in our arithmetic. Unfortunately, in general, in this arithmetic, there's no unique way of factoring. So this brought Kummer to a great development, the invention and study of ideal class groups in general. So the idea is you take ideals in this ring, Z zeta, that is abelian groups that sit between some multiple of Z zeta and Z zeta itself, such that they're preserved under the action of the ring. So alpha times that abelian group is again inside the abelian group. And then you have special ones which are called principal ideals, which are just multiples of one particular element. So in this way you have certain things attached to this new arithmetic, this arithmetic of Z zeta. Well, what he showed was that if you study what's called the ideal class group, that is the quotient of the group of ideals over principal ideals. It's not quite a group, but the quotient is a group, ideals mod principal ideals. He proved first that Fermat's last theorem is true if P doesn't divide the order of this group. So he gave a very explicit criterion for proving Fermat's last theorem. Well, of course, could be quite hard to calculate this size of this class group. So he gave a second criterion, which is even more amazing in a way, which is that P divides this order of this class group if and only if P divides the product of these Bernoulli numbers, B2 up to P minus 3. These Bernoulli numbers are the numbers you get by expanding T over e to the T minus 1 as a power series. And they're the coefficients of that power series, 1 plus the sum of Bm T to the n over n factorial. So he gave this amazing analysis, not only of the equation, but actually of the obstacle to solving the equation. All attempts at Fermat's last theorem up to the end of near the end of the 20th century really hinged on this technique and on trying to refine these properties of these class groups. Was there something about class groups we're missing? Can you prove more about them? Because unfortunately, this wasn't enough. It's very, very hard to determine when P divides these, and it certainly happens often. In fact, one of the things I studied, my last fling, as it were, with Fermat's last theorem by the old methods, when I was working with Maser at Harvard, we analyzed the fine structure of this class group to actually determine a relation between each individual villa and some piece of this class group. But these methods were not enough to actually master the original problem. It's still, there was a gap between what we could even hope to do and the resolution of the problem by this method seemed completely inaccessible. So this is, as I said, how the subject proceeded for a long time. Now I've called this the abelian approach to Fermat's last theorem. So why do I call it abelian? What's it to do with Abel? Well, it's to do with abelian extensions. So Abel, the name abelian, is attached to extensions of the rationals or other fields where there is a Gauer group and the action is abelian. So for example here, and we were using arithmetic with zeta or zeta p, I'm writing here, p through to 1. So that's a root of this equation, x to the p minus 1 over x minus 1 is, well, this is another way of writing it, some root of that, it's 0. So it's abelian because the Gauer group of q zeta p over q, it's the rationals that join the zeta p, is described as the abelian group z mod pz cross. That's the multiplicative group of z mod pz. How does that work? Well, a typical automorphism in here will take zeta p to some other p through to unity. It has to be a power of zeta p. Write it as the lth power, and that goes to L mod p. So this describes the Gauer group explicitly, and the Gauer group is abelian. This describes it as an abelian group. And this sigma L came to be known much later, if L is a prime, as the Frobenius at L. We usually write it Frob L. Well, these are abelian extensions, and this, for a long time, became perhaps the central study of number theory. Partly inspired by a theorem of Kronecker and Weber. They didn't work together. In fact, they were separated by quite a long time. This took a long time to actually get properly proved that, in fact, all abelian extensions of the rational numbers are generated by roots of 1. So that's two statements, really. One, that fields generated by roots of 1 are abelian, and that's the easy part. And the hard part is that every abelian extension arises that way. Well, this takes us, the Kronecker-Weber theorem, to nearly the end of the 19th century. The first part of the 20th century was spent in generalizing this abelian theory to other fields. And this is known as class field theory, and this is really the sort of centerpiece of number theory for much of certainly the first half of the 20th century. So to describe abelian extensions of any number field, let me just take an example. Whoops, sorry. An example of F is the field generated by the cube root of 2. So what you want are abelian extensions of that field. So it's actually very hard to write down some simple description like using roots of unity. So that we haven't really mastered in any generality, although it's still a problem, an open problem. What we can say is what exists. So we can say that there is an extension which is similar to Q zeta p, plays the same role, and it has the property that the Gauer group of this field, which I've called FP, so the FP just means it's just a labeling for this field which I claim exists. The Gauer group of FP over F is isomorphic to the integers of F modulo P times the integers of F, the multiplicative group of that, modulo the image of the units. So OF of the integers, that's Z cube root of 2, and this group OF cross plus of the units, or positive units of OF. So this took the first 25, 30 years of the 20th century, but to really formulate it well took at least until the 50s, even 60s. It's much more complicated when the ideal class group of OF is not 1. So in the cases that Fermat was worrying about, I mean not Fermat, but Kummer was worrying about, it would be much more complicated. So of course, when you spent so much time developing the theory of abelian extensions, one wants to move on to the non-abelian extensions. And this is the great split. And in the second half of the 20th century, a huge program was developed to try and understand these extensions. So they're basically equations over the rationals or over another number field where the Gauer group is not abelian, where it's perhaps even a non-abelian simple group. And the fundamental description of this, what it should be, it's still conjectural. It comes from what's called the Langlands program. So there's a decisive shift to this in the 1960s, and there are many, many problems in this area, which many people work on, and we've made a little progress in this context, but not very much at the moment. It's actually easier to describe the parallel progress that this generated on the Fermat problem itself. So I'm going to switch back now. So this was how number theory is developed. But now the non-abelian approach to Fermat itself. So this big breakthrough occurred in 1985 and was suggested first by Gerhard Frey. And then it was, the actual connection was completed by Ribbit a year later. So the idea is this, and it's a completely different idea. Supposing you have a solution to the Fermat problem. Wrong one. Okay. New idea. Suppose a to the p plus b to the p is c to the p. P, I'm just going to assume p is prime. The Fermat problem is enough to do it for prime exponents, so we usually just restrict to those. Then you manufacture artificially this new equation, which is equation of elliptic curve. Y squared is x minus a to the p, x plus b to the p. Okay, seems harmless enough. It's odd because you take the discriminant of this cubic, it's that's of course the product of the difference of the roots squared. So it's a to the p, b to the p, and then a to the p plus b to the p, which is c to the p by hypothesis. So the discriminant turns out to be a perfect pth power. Okay, so elliptic curves have been studied a lot, and this seemed very odd, to find a discriminant which is a perfect pth power. And in fact, what Frey realized was that such a curve should not exist. Discriminants should not be pth powers. So he proposed a way that you might try and prove this. It was a bit tenuous at first, but Ribbit, as I said, confirmed that in fact, if you assumed what's called the modularity conjecture, the Taniyama-Shimura-Hey conjecture, it has various names, then in fact you would have a concrete way of proving Fermat's last theorem. If you could show there's no elliptic curve of this form, you prove Fermat's last theorem, and to show there's no elliptic curve of this form, you can use the modularity conjecture. So this gave a completely different approach. So just to give a little hint about this, I need to just say a tiny bit about elliptic curves. Again, the origins of this subject are in Abel. Abel was the first to really understand, talk about these doubly periodic functions. He died at 26. Maybe he could have done all this if he'd lived longer. It was so fast. So supposing you take an equation of this form, y squared is x cubed plus ax plus b, what elliptic functions enable you to do is to describe the complex solutions to this as a group. It's C modulo a lattice, an abelian group of the form Z plus Z times another generator. This tau is not itself rational. And then this quotient actually forms the complex points of this curve. Well, one thing that's very odd about this is that this is actually a group. That's not at all obvious when you look at this equation. So the solutions to this equation actually form an abelian group. And if you draw C mod the lattice in the plane, then it's basically the interior points with some of the boundary described like this. Okay, in particular, you can ask about points on this group of finite order, and the points of order p to the n have the structure z mod p to the nz plus z mod p to the nz. Didn't understand why, when he looked at this, he got n squared roots instead of n roots. Now it's clear, but he wrote in his correspondence that he was mystified by this. He understood it after a little while. But. So if this equation is actually defined over the rationals, you can actually get a Galois action on these points. So the Galois group of the kernel of p to the n, that's the c mod p to the n plus c mod p to the n. The Galois group gives an action, so it injects in GL2 of z mod p to the nz. So what is this? Okay, this is background on elliptic curves. We haven't quite got enough to understand how to apply this to the Fermat equation yet. So I want to just specialize the case p equals 3. So this was, in some sense, the first big step, well, the first step that I described yesterday in tackling Fermat was to understand, was to choose an arithmetic approach, which, as I said, there's different ways of approaching this modularity conjecture through geometry, through arithmetic, through analysis. So I chose arithmetic as that's what I knew about. But then the big choice was actually go to p equals 3, because if you look at the 3 division points, so I've put them on, these are the 9 3 division points in here. Algebraically, you can actually describe these, if you take the equation y squared is x cubed plus ax plus b, these are actually the points of inflection, just in classical calculus terms. If you calculate the points of inflections of that equation, remembering you're not just talking about real points of inflection, there's actually 8 of them, and then you get a 9th one at infinity. They actually themselves form a group, there's 9 of them. And they generate a field QE3, and the Gauss group of QE3 over Q then acts on GL2 of Z mod 3Z. So this is just the same as in the case P. General P, just specializing to P equals C. What is special about this is that, okay, it's not abelian anymore. This is not an abelian extension of the rationals. But happily for me, it's also a solvable group. This group, GL2Z mod 3Z, is actually a double cover of the symmetric group on 4 letters. It's a solvable group. So Whereas Arbor thought in terms of there was a division between equations up to the quartic, where the equation was solvable, and equations of high degree in the language of Galois, which might not be solvable. I'm actually considering three distinctions as the abelian groups, the solvable groups, and the non-solvable groups. The non-solvable groups are extremely difficult, and as I said, arithmetic hasn't got there yet. But this realization was that actually this in-between stage, a solvable stage where I could perhaps squeeze through. Okay, so that's elliptic curves, and then the modularity conjecture, so I have to say what it is, tries to link what are called modular forms, or modular functions, with elliptic curves. So modular functions have been studied in the 19th century. They're actually a generalization, if you like, of the exponential function. The exponential function has the property that it's periodic. If you take e to the 2 pi I z, it takes the same value when you move from z to z plus 1 to z plus 2 to z plus 3 and so on. And this is the basis of Fourier series and Fourier analysis and so on. But again, that is the abelian situation. And the non-abelian situation is when you move to functions which are invariant not under z, under the abelian group, but under a non-abelian group. In this case, a subgroup of SL2Z. So these functions, yes, they have a Fourier series. They are invariant under z goes to z plus 1. But they also have this other property that if you take f of az plus b over cz plus d, it's, well, we allow something slightly more general in the case we want, is c to the z plus d squared times f of z. That's whenever the matrix A, B, C, D is an element of SL2Z with the C divisible by some integer n. So for all ones that A, B, C, D with C divisible by n. And just so long as you can choose an n where it works, that's what matters. So this is a generalization, the non-abelian generalization of exponential functions. We get modular functions like this. So everything is moving from the abelian situation to the non-abelian situation. So the modularity conjecture of Taniyama Shimura was that there's some correspondence. Every time you have an elliptic curve over the rationals, you can actually make a modular form of weight 2, that's the 2 here. So I haven't, if the weight is, but it just means this factor here. And some level, that's the n. So the weight 2 means here and the level here. It doesn't really matter in detail for the moment what they are. And what is this correspondence supposed to do? It's supposed to say that when you take the Galois group and the Galois action on the p to the n division points, so view that in GL2 of z mod p to the nz, because that's what the action on the p to the n division points looks like. Under that, the Frobenius of L, well, I described to you earlier, there's a notion of a Frobenius, so I described it in the abelian setting on roots of unity. It takes zeta p to zeta p to the L. It's actually a bit more tricky to describe it in this non-abelian setting, but there is a generalization due to Frobenius, it has its name, that for every prime L, you have a Frobenius of L. And under this correspondence, it goes to an element with trace AL. AL is the AL from here. So the Fourier expansion of this function tells you about the arithmetic of the elliptic curve. So this is the arithmetic of the elliptic curve, the Galois action on these p to the n division points. This is the modular form. You look at its Fourier expansion and some magical relation between the AL here and the Frobenius in the arithmetic. So this conjecture seemed, when it was first proposed, in a vague form by Taniyama, got made more precise with Shimura. But it was Wei's paper of 1967 where he pinned down the level n and proved a very beautiful theorem about it that enabled people to test it. So they could test this conjecture numerically, and they got overwhelming evidence. People were convinced this was true. So now, when Ribbit had proved that the modularity conjecture, this one, implied Fermat's last theorem, we now could be really confident that Fermat's last theorem was true, that it would be proved, and that it could be proved this way, because this modularity conjecture, it's not something mathematics can put aside. Fermat's last theorem could have been like perfect numbers. It's put to one side. We can get on with mathematics without it, but we can't get on without this. This is at the core of the transition of number theory from non-abelian mathematics, from abelian mathematics to non-abelian mathematics. So Fermat's last theorem was back right on center stage. Okay, so what is the outcome of this? Well, as I said, as soon as I heard that Ribbit had proved this connection, I was riveted and spent my time working on this. So why does the case P equals 3, why is it so valuable? Well, the point is, what have we got? So we have Frey and then Ribbit proved the modularity conjecture implies Fermat's last theorem. So now the problem just proved modularity conjecture. Okay, and as I said, when I started trying this, the first, after the first step of taking the right choice, making the right choice to go into arithmetic, I think the first real conceptual important step is that if you look at the 3 division points, whoops, I put GL3. It should be GL2, Z mod 3Z, PGL2, Z mod 3Z, is isomorphic to S4. This is a solvable group. And when Langlands had proposed this general program for understanding non-solvable extensions, there was one case that he could really understand, and that is precisely this, when you have Galois groups of the rationals into, or even any number field, into a solvable subgroup of GL2, and S4 is such a subgroup of PGL2. S4 is such a subgroup. So what Langlands, and actually this particular case is an extension of Langlands' theorem by Jerry Tunnell, this is connected actually with the modular form. It's not the one that we want associated to an elliptic curve. It doesn't solve the problem right off. But at least it gives you some tenuous link between the theory of elliptic curves and this theory of modular forms. He based this on his theory of phase change. And it uses the fact, as I said, that S4 is a solvable group. So this was remains the first step. There is no way around this step at the moment. We have no way of jumping straight to non-solvable extensions. The only entry point we have is via these solvable extensions in the middle. So abelian extensions we understood in the first half of the 20th century. We pushed that a little further to these solvable extensions like S4. And we can use that to get a little bit further, but we really have not mastered these completely insolvable extensions, these simple groups of any kind. Well, let me just say a few words about this generalization of Langlands, which lots of people work on in number theory. It's really, as I said, the main thrust of modern number theory, because even working on other problems like elliptic curves and any kind of generalization of elliptic curves, you want to solve equations, you're going to have to use this ultimately. So it's a generalization of class field theory. Remember, class field theory describes abelian extensions. Here the problem is to describe all Galois extensions of the rationals or any number field. And roughly speaking, and I'm being dishonest, but roughly speaking, it generalizes modular forms to automorphic representations. And roughly speaking, we use functions invariant instead of under subgroups of SL2, but under subgroups of GLN to classify n-dimensional representations of the Galois group. So it's a very beautiful idea that you can do this. Now, it's slightly dishonest because you really have to use Adels and adelic representation theory. But this is back to classical number theory, where you use analysis and now also naturally representation theory to study number fields. We've been very lucky to have the assistance of algebraic geometry for 50 years, and it sometimes has blinded us. The fact is, Langland's proof did not use algebraic geometry. It's just analysis and representation theory. Langland's proof for the S4 case. And this general case is still completely baffling to us. So let me just mention there's a little progress. So one of the simplest ones you might try and understand is the Galois group. The representation of the Galois group Q bar over Q to GL2 Z mod LZ. So this group is not solvable. But if you assume the determinant is odd and rho is irreducible, then rho is associated to a modular form in the sort of way I've been describing. The proof uses similar techniques. Again, the entry point, you have to enter via these solvable extensions. So you enter this theory using Langland's theorem, using also the reducible case, but then a very, very ingenious induction on primes. They managed to push these techniques to prove the modularity, so association to modular forms of these kinds of extensions. So this corresponds to extensions of the rationals with certain kinds of Galois group that sit inside GL2 of Z mod LZ. But this is still a very, very special case of the Langlands program. Unfortunately, the method doesn't seem to work in the general case. The general case would be GLN, or even any other group, and any number field in place of the rationals. So we are at a stage we feel we've mastered the abelian setting. We would really love to understand the non-solvable, even the simple group setting. We're just piecing together some results about the solvable case. But we have a few istalts like this in the genuinely non-solvable case, but we're still at the very beginning of this great enterprise, the Langlands program. Thank you very much.
Thank you very much for your exciting lecture. You mentioned that one of the key ideas in the whole presentation was Frey's idea to construct an elliptic curve, which is now called the Frey curve. Frey told me at the time that he thought this was some kind of joke to reduce one unsolvable problem to an even more difficult and more unsolvable problem. Obviously, he was proved wrong, but I would like to hear your idea on how much you perceived this as a joke or whether you felt immediately this was realistic and there was a chance.
Sorry, who said it was a joke? I missed that.
Frey himself.
Oh, he did.
He said he proposed it as a, well, he felt it was a joke to reduce something unsolvable to something even harder.
Yes, I didn't know he said that, but actually, there was an even more painful story. I think that Helleguard, some years earlier, had studied similar equations and had wondered if they were related to Fermat, or he'd shown them to a very eminent mathematician who'd said that's ridiculous, you might be able to do Fermat that way. And so he'd given up working on it, according to him. So, yes, I think that does happen. I have to admit, when Frey made this proposition, I actually was very skeptical, not about modularity conjecture, but about what Ribbit proved. So I was very surprised, but very happy when Ribbit proved it. I thought it was just wishful thinking, but yeah.
I would like to return to the elementary and the beginning.
Yes.
You said that Fermat himself solved the problems for n equal to 3 and 4. And I suppose that after that there was a hunt for solving it for individual numbers or classes of numbers bigger than 4. 5, for example.
Yes.
Could you say a few words of how that
Yes. So
went on?
the first one to really pick up on it was Euler, because the proof for n equals 3 had not been written out. So Euler did the case n equals 3. I think he made a mistake the first time, but I think he corrected it. So the next one was n equals 5, and that was very tricky. You can try and do it the same way, but it's much more complicated. And I believe the story is that, I quite like this story, my age, that Dirichlet was in his early 20s and did one part of it, what's called the first case, I think, of the problem. It's since, it's now called. So he did one case, but he didn't complete it, but he somehow was talking about it. And Hermite, I believe it was, at 70 years old, I think I've got it the right way around, came in and beat him to it. So I think it's but those two. So I think the case n equals 5 was done. The case n equals 7, I think this precipitated the problems of the French Academy, because I think Lamé claimed a very complicated proof and was announcing it to the French Academy, and some of the other mathematicians, like Cauchy, got very excited and said, yes, I can do that too, and I can do this. And unfortunately, I think this was where the mistake was, the unique factorization problem. He hadn't sorted it out. He'd made some assumptions, so I think eventually the case 7 was done in hands-on methods, but I've forgotten the details. But anyway, there was an attempt at various low prime numbers. But then when Kummer's work became known, Kummer's methods did all primes less than 100, except for 37, 59, and 67. Unfortunately, Commons methods couldn't even be used to prove it worked for infinitely many primes, I don't think. So it stalled. I mean, it looked very promising for a while, but then it stalled.